Oh, it's on the website. Oh, it's not linked? Oh my God, I'm so sorry. Oh, it's at the bottom. It's at the bottom. Yeah. Yeah. Come here, come here, come here. Down at the bottom. Sorry. Yeah, the slides have a hyperlink attached to them, but not this. I apologize. But yeah, it's down here. It's down here at the bottom. Yeah, it's gonna be just on Gradescope. It's not gonna be like difficult or anything. It's just gonna be just like did you proof of work effectively. Just to make sure that you actually like tried to run a training, just submit some kind of the log effectively. Just a screenshot of that. Because this first assignment is more for your benefit than anything else. Just because it's going to teach you the tools that we're going to use for the rest of the course. Okay. Are there more questions? If not, we can jump straight in. All right. Yeah, I guess some quick announcements. We have the coding assignment due next Tuesday. We got it out a little bit late, so I won't begrudge you if you turn it in slightly late. The first quiz is also due tonight. Again, same story. If it's a little bit late, that's not the end of the world. But it should just serve as some kind of a comprehension check, just to make sure y'all like paid attention, like stayed awake during lecture. Yeah, it should be integrated with feedback shown, and if it's ever not, like, please yell at us. Because yeah, it's not meant to be hard, and it's not something you're really graded on. It's just completion. What was that? It was supposed to be due tonight, but I'm not going to begrudge you if you turn it in a little bit late, because we got it out kind of late too. So just on completion, it corresponds to last week's lectures, so hopefully you should be able to complete it. Yeah. Are there more questions? And then we can all right. Then let's jump into this. So this is the first half of lecture is going to be on, we had some questions about like how does one actually like calculate these partial derivatives? This is just sort of some culture as to how this actually happens, like under the hood. If it goes fully over your head and you space out for the first half hour, like it literally doesn't matter, so long as you can still use the tools at the end of the day. But this is just sort of to answer like how it's actually done under the hood, how we calculate all these partial derivatives of our gradient. And then the second half is going to be actually important stuff. What different sort of tools to add to your toolkit for modern deep learning stuff. And then if we have time at the end, I can show you guys PyTorch, the tool you're going to be using all throughout this course to actually code up neural networks and use them. So again, just a warning for this first half of lecture, we're going to be discussing backprop or the backpropagation algorithm. And if you don't get it, if you only catch like the general gist of it, like that's totally fine. It's all good. The only thing is really, again, just that you understand the high level idea of like what it's doing and why it's important. The second half of the lecture, though, I really do want to make sure we spend enough time on because it's all of the things that make modern deep learning work really well. Yeah, so at any rate, the first half. So deep learning review before we get started. This is from last week's lecture. Our neural network is just a function of scalar parameters that are contained in our weight matrices and our bias matrices. And we can take the gradient, just the direction of steepest ascent, or if you go in the opposite direction, steepest descent of our loss function with respect to all of our just scalar parameters, and effectively step our weights and biases in a direction that slowly, hopefully, decreases the loss of our network. Simply just subtracting a small scaled version of the gradient is what we're going to be doing. The gradient being evaluated for our current data and our settings of our parameters. So this is going to be kind of the core idea of backprop, is just sort of creating a computational graph for our functions. So say we have a function C, which is a function, I'm sorry, a function E of two parameters, C and D, but C and D are in themselves functions of other parameters, in this case, A and B. We can write this all out as a computational graph, depicted here on the right, where every single function is depicted as a node, and all the parameters required lead into that node. And the operation, that little function, is written on the node itself. So we can create this little tree here for functions of many more functions if we want. So this is sort of what it looks like. We call this a computational graph. It tells us how we can compute E, given our starting values, just A and B. And if you want to do calculus, so say you want to know the partial derivative of E with respect to something else on this tree, you can use the chain rule, which simply tells us that if we look at every single path to get from, say, in the case of this down at the bottom, to get from B all the way up to E, if we go on every possible unique path and multiply by all the partial derivatives between nodes along the way, we can get the partial derivative of any node, any final node with respect to like any input node. So this is just a way to write out the chain rule that many of y'all learned in like Math 53. It means that we can just calculate the partial derivatives with respect to adjacent nodes instead of having to calculate partial derivatives over long distances. We can use all these little individual components, like the partial E with respect to C and the partial C with respect to B. Use all these little individual components to get a larger partial derivative that spans a larger distance on this graph. It's just a more interesting way to think about the chain rule, really. So are there little questions on that, on the chain rule for multivariable calculus? All right. So that's the primer required basically for backpropagation. So to start about what backpropagation is, we have like a little example here. This is a toy neural network. Our W's and our B's are just, they're not even matrices and vectors, it's just single scalars. So we have a neural network with exactly one unit at each hidden layer, and one bias term to accompany that. So our W1, our B1, they're just simply scalar values. They're not even matrices, not even vectors. One neuron per layer. And we want to compute the loss with respect to our parameters, or the derivative of the loss with respect to all of our parameters. So we need to calculate the derivative of L, that node on the right, with respect to B3, with respect to W3, E2, W2, B1, W1. But we don't really want to do like a ton of redundant computation. Like this is 6 different partial derivatives that we need to take. And we want to make sure that we're doing this efficiently, because in the more generic case where we have many parameters, this is important. So we want to make sure we're not doing 6 times as much computation to calculate 6 gradients. So if we want to write out the chain rule for all of these, we'll end up seeing that this allows us to kind of optimize and like save some computation. Because again, this is just a computational graph, right? Just like we saw before, and you can take partial derivatives with respect to individual nodes that are next to each other. So if we do this, and this looks a little bit complicated, but I assure you it's not. It's just the chain rule again. So if we want to take the derivative of L with respect to W3, our first weight parameter, that's simply the partial derivative of L with respect to the node Z3 multiplied by the partial derivative of Z3 with respect to W3. There was exactly one path on our computational graph from W3 to L. And we just multiplied all the partial derivatives along that path. And we did the exact same thing for L with respect to W2 and L with respect to W1. You can see that the deeper we go into this network, or the farther back we go from L all the way back to W1, the more things we have to multiply out. But if we look here, a lot of these multiplies are like the same. So this value boxed in red on the left there gets reused as soon as we go to calculate the partial derivative of L with respect to W2. And then you'll notice that entire thing boxed in blue is reused when we recalculate, or not recalculate, when we calculate the partial derivative of L with respect to W1. So there's a whole bunch of redundant computations being done the farther earlier in our network we go. And backpropagation is very simple. It's just that as we go and calculate all of our partial derivatives, rather than recalculating the stuff in blue over here, let's just cache it when we're calculating the partial derivative of L with respect to W2. That is the core idea of backpropagation. Rather than recalculating values and doing repeated multiplication, redundant repeated multiplication, we should just save compute from the first time that we went and calculated our partial derivatives. And it saves us a lot of redundant multiplies when we go to calculate our partial derivatives. We simply work our way from the back of the network all the way to the front. And you can imagine in general that now W be our matrices and vectors instead of just individual scalar values. In that case, all of your derivatives are now going to be derivatives of scalars with respect to matrices, which is scary. So I don't want you to think about that too much. But my hope is that you understand that now all these partial derivatives involve matrices, and our simple scalar multiplications have now become matrix multiplications. So this caching becomes even more important now, because now, as opposed to now, we're saving matrix multiplies, which are very expensive operations in general. And it's important to kind of cache those where we can. So it's the same idea as we saw before, only now these derivatives are going to be of scalars with respect to matrices and matrices with respect to matrices, which again, if you don't want to think about that, don't bother, it's all good. But again, we're now saving matrix multiplication operations as we start caching all of our multiplies. So that is the big thing I wanted y'all to take away from this. Backpropagation is simply a much faster way to get all of our partial derivatives required for our gradient without having to do a whole bunch of redundant operations. Simply caching things as we go, working from the back of the network, from L all the way up to the front to our initial weight matrices and bias matrices. Does anyone have questions, comments, concerns about this? I know last week there were like questions on how do we actually go about calculating all of these derivatives for our gradient vector, and hopefully this kind of lets you kind of peer under the hood a little bit and see how this is working. How do we know what values to cache? So you can see that as we're going back, we have just like this running value, like we have the value box in red, and then we're going to multiply two more terms out. We're going to teach you PyTorch, which is a tool that will do all of this automatically for us, cache all this stuff as we go. But yeah, that is effectively it. PyTorch will figure out what it needs to cache in order to do this efficiently. But the hope is that you understand, you can see the need for caching things as we're going back, and you can imagine how this gets even worse if we have even bigger networks and so on. Are there any more questions or comments or concerns about backprop? And again, this is kind of weird. And if you're not super familiar with the multivariable chain rule, that is like totally okay. Yeah, it's not going to affect the way in which you create neural networks, because again, we have tools that take care of all this for us for free. But the idea of a computational graph and graphing out how all of our different parameters are related, how they all interact with each other, is a useful tool when you're thinking about how to build systems. So with that, unless there are more questions I can take, we can run through modern deep learning, which is definitely important. All of these things, I think, in here are prolific throughout the field, and they make the standard version of a neural network, the most basic version of a neural network that we saw, worked far better. Yeah, and hopefully they answer some more questions that were had from the previous lecture as well. So yeah, let's jump into it then. So optimization, and we do a little bit better than vanilla gradient descent. There were questions last week, like someone asked, what happens if gradient descent is descending a hill? What happens if there's a little bump in the hill? If we're going down a hill and all of a sudden we hit this little local minima, how are we not going to know that there's an even better place we could have landed down here? And with vanilla gradient descent, the answer is this is definitely a problem. Or just flat spots where we can't seem to get past because our gradient here is 0. We have no direction in which to move. So these are like problems that vanilla gradient descent has. Oh, and also to emphasize, with these things, it's fully okay. I have the equations so that if you want to go back and look at it later, you can. But if you don't want to look at the equation, that's fine. Just make sure you understand the high-level takeaways as well, I would like to add. So momentum is one way in which we can improve gradient descent. So we'd hate for these little small local minima to screw us up. So we're going to take inspiration from an actual ball rolling down a hill. If you roll a ball down a hill, it has momentum. So as soon as it comes down to the bottom here, it's carrying with it plenty of momentum. And objects in motion tend to stay in motion. And it has the energy enough to climb up the hill and hopefully get down to a better local minima. So what we are going to do basically is take all of our past gradients and simply add on to whatever gradient we're about to do the weighted average of all of our previous gradients. And technically, we are no longer doing like true gradient descent because if we have hit the bottom and we start climbing up the hill a little bit more, we're moving in the opposite direction from the true gradient. But that's sort of okay. The hope is that by adding this little thing onto our normal gradient updates, we're going to be enabled, hopefully, to climb over little hills, push past any big flat spots. And again, the core idea here is that we're simply going to add to our gradient update just the previous weighted average of all the gradients that we've been taking. So you will continue to move in the direction that you have been moving in the past, with the idea, again, that you can power through little local minima and flat spots. Are there questions on this? Yes. Scale it down. Oh, are you talking about the betas? Yeah. Yeah, so that's just that just lets us do a weighted average. So what that line is there, the first line. So before previously we were subtracting off just the gradient component of this parameter, the partial derivative. So now what we're subtracting off is the weighted average. So if you think about it, our previous gradients, say I'm trying to think how to describe this well, but the bottom line is if your previous gradients are like non-zero, if your previous gradients are like, they've been averaged out, right? If you multiply them by like a scalar, say like 1/2, and then you multiply your current gradient by 1/2, the resulting value that you get, you've scaled two components by 1/2. So when you add them both together, you're getting something that's about the same size. So say your previous gradients had a magnitude of like 1. Say your current gradient has about a magnitude of 1. Your concern, if I understand correct, is that we've now just shrunk our gradient even more. If our previous gradients on average had about a magnitude of 1, and our current gradient has a magnitude of 1, let's say like beta is equal to, in this case, like 0.3. If beta is equal to 0.3, we're going to multiply our previous gradient, our history of gradients, by 0.3. So that quantity has a magnitude of about 0.3. And then we're going to multiply our current gradient by the remainder of that, which is 0.7. And if our current gradient has magnitude about 1, the resulting quantity that we're then going to subtract off of our parameters our resulting sort of effective gradient, our gradient with momentum, will have about the same magnitude. Does that sort of answer it? If not, I can try and go again. Explain it differently.
No, yeah. If we're thinking about how a ball is going down kind of hill,
Mhm.
right? As like the steeper the hill is,
Yeah.
the faster it's going down. So that's
Yep.
what we're thinking in that sense. But how is that kind of like showing, kind of like our vector or like our balls like momentum? Is that what you mean?
The betas are simply to make sure that we're not like making our gradient too big. Because say like we didn't have betas and we've been rolling down the hill, and we have a lot of momentum. Like, okay, say it's not even say it's just a straight line down the hill. The hope is that, so we're gonna start here, we're gonna make a gradient update, and we're gonna move down to here. The hope is that the next step we make will be about the same size if the hill stays constant. But so I guess, yeah, you're right. If this was true to momentum, the next step we take would be even bigger, and then after that, even bigger. But the reason that we have those betas is just to control that so it doesn't get like way out of control. We just want to take consistent steps if our hill stays the same. But that momentum will still be used if the hill instead went like this. We would have the history of taking step sizes about that big. So even after we fit this little local minima, we'll continue to climb. So yeah, I see your point. So in that sense, it is a little bit different from momentum, in that our step sizes don't keep on growing like crazy. The betas are just to kind of control that a little bit and make sure things don't get too wild. But the momentum thing still applies. If you have been moving in one direction, you will generally continue to move in that direction over time. Does that sort of answer your question?
Yeah.
Okay. Yeah, good point. So you can see on the top, we have a loss surface. So say this is a hill. On both of these graphics are hills that we're trying to descend. The kind of darker area is lower and the lighter areas are generally higher. It's basically like a topographical map. If you've ever seen like a map that tries to have little elevation lines, it's the same idea. So you can see without gradient descent, we're going to move in the direction of steepest descent, which jumps us over this little, canyon. And it keeps ping-ponging us back and forth, back and forth, back and forth. Momentum, we're moving slightly in the direction towards our local minimum. So the next step we make, we're going to move slightly towards that direction a little bit more, and a little bit more, and a little bit more. The direction in which we have historically been moving over time, average, is the direction we're going to continue moving in. And you can kind of see that in how, with momentum, we move towards the local minima far quicker, instead of just oscillating back and forth, moving in the direction of the true gradient. Yes, friend. Yeah. Yep. Yep. You're taking the weighted average of all of our gradients, and yeah, as we start to, say we hit the actual bottom, rock bottom, we're going to start going up again. But because historically, after we've started moving this way, our gradients will point this way, right? We still have momentum, so we're going to go a little bit further. But the more and more times that we sample over here and take gradients from over here, we're going to start sliding back a little bit. And the hope is that we kind of slowly settle in there. Does that answer your question? Okay. Are there more questions? All right. So the next kind of optimization method we can use that's a little bit different. The TLDR of it will be on the next slide, but this is just explaining what it is. It's called RMS Prop. What we're basically going to be doing is, instead of storing a weighted average of all of our previous gradients, we're going to be storing a weighted average of all of the components in our previous gradient squared, all the components squared. we're just going to keep holding on to the moving average of our squared gradients, or squared gradient components rather. That is the basic idea. And when we actually make our update, so you can see down at the bottom, this is basically our vanilla gradient descent, except for that we're dividing by the square root of the square of our true gradient, which is a little bit unintuitive, but we will explain sort of the reasoning for why this would work here in just a little bit. And we also add this little epsilon before we take the square root of it, because if we really want to make sure we're not dividing by 0, or before we divide, we're going to add a little epsilon. Just as sort of a computational note. Epsilon is just a really small arbitrary number. Again, just to make sure we don't get divide by 0 errors, because that's frequently problematic and will cause our program to crash. But it's so small that it doesn't really affect the value. So that is what we are doing mechanically. So why would this work? So think of like 2 specific cases here with gradient descent. In one case, our gradients have historically been very small. You can think of that as this example right here. Say we've hit a flat spot, and our gradients have a history of being super tiny, whereas here they were much larger. So the square of this history of super small gradient components will be even smaller. If you square a small number, it gets way smaller, is the basic idea. And when you divide by said increasingly small number, that'll sort of boost our gradient a little bit. So if we have a history of really small gradient components, as soon as we square, if we keep the history of the squares of this history of small gradients, that number, it just becomes incredibly small. Even after you finish taking the square root of it, it still is just absolutely tiny. So once you divide by that number, it's going to boost our gradient. So our gradient becomes much bigger because when you divide by a very small fractional number, that has the effect of increasing the value in the first place. In the second case, if anyone has questions on that and wants to interrupt me, I can take them too. The second case is, say our gradients have been super big. Say we have something that just looks like that. Our gradients are huge. Because they're so huge, we are about to wildly overshoot this minimum. If our gradients have a history of being extremely big, when you square all of those components, they're going to become even bigger, right? And then as soon as we divide by that number, we are going to get a much more reasonable scaled down value. So if our gradients are way too big and out of control, RMS Prop, as soon as we divide by the history of square gradient components, we're going to get a value that's a little bit smaller and a little more reasonable and keep us from wildly overshooting our minimum. So RMS Prop is really good at handling cases where our gradients have a history of being really extreme. Either we're in sort of a flat spot and they need to be boosted, or our gradients are way too big and are going to cause us to wildly overshoot the value that we want. And it sort of allows you to, previously with vanilla gradient descent, if you wanted to get around this, the issue of a flat spot, you had to have a really high learning rate, which might be suboptimal. It might help you get through these flat spots to have a really high grade or have a really high learning rate, to be updating our parameters by a lot. But then as soon as you get out of that flat spot, now your learning rate is way too big. And in this case, if you have a history of having a lot of hills, having a really low learning rate might be nice, but it might also take forever as soon as you've gotten off that huge hill. So RMS Prop means, your choice of learning rate, the amount that you're updating our gradients by, that constant lambda, isn't really as big of a deal. And it sort of, you can think of it as like an adaptive learning rate. Yes? Yes, you jumped the gun. Adam, are there more questions before I move on to? Fantastic question. You read the slides, didn't you? So if there are no questions, I'll keep rolling on. Adam is basically the best of both worlds. it gives us the benefits of both. And out of the box, when you're using PyTorch and you can select an optimizer, just choose Atom and leave the parameters as default. It works good pretty much everywhere. It's just fantastic. It is the preferred method of gradient descent. It basically combines RMS Prop and momentum. We keep track of all of our previous gradient updates, the weighted average, and we also keep track of our history of squared gradient components, just like we did in RMS Prop. And just like with momentum, we're going to sub out our gradient update with the momentum included gradient update, and we're going to divide that gradient update by the square root of our weighted average history of squares, giving us the benefit of both is the idea. And again, if it's complicated, like that's fine. If it looks complicated, no biggie. The thing I want you to take away is that we get the benefit of being able to roll through little local minima, just like with momentum, while still being able to account for issues like this, where we have really flat spots and we want to boost through them, or we have really steep spots and we want to slow down, so we want to wildly overshoot a minimum. So that's sort of the idea of Atom. And it just use it is the takeaway. It's fantastic. Are there questions on this? Yes, Fran?
So does RMS Prop not already solve the momentum problem when you have the square gradient? Like, isn't that still giving you some sort of momentum?
It doesn't change the direction of your gradient.
Right.
All it does is change the scaling of it.
Okay.
So yeah. So if you're right here, it's gonna, yeah, it just changes the scaling, but not the direction, whereas momentum will actually update the direction. Good question, very good question. Are there more questions or comments? Yes, friend?
So you're actually
yeah. Oh yeah. I mean, it can be. I suppose if you're actually at the minimum and your gradient has a history of being 0, yeah, that's a good point. RMS Prop is good for getting to the local minima, but after it gets there, it might be problematic. So if you generally just keep a history, if you're keeping track of all of your loss after every iteration, you can actually just like do something called model checkpointing, which is sort of important, which is just save your model every once in a while after each iteration, after you've gone through your data set once. Just see how well it's doing, evaluate it, figure out what the loss is on like some validation, some new data that our model hasn't seen before. Save it, right? So yeah, if say we've hit a point like this, our loss has like gone down over time, but now it hits this value of 0 and it starts acting erratically and our gradients just go nuts, right? Because our history of gradients squared is so tiny, you might see your loss function like jump up again and start doing weird shit. So just if you're keeping track of your model's parameters after every iteration and just saving them, at the end of the day, all that matters is that you have a model that works on new data. So if you have your history, your model's history saved, you can just pick the best model, basically. But yeah, fantastic point. RMS Prop is good for getting you there, but once you're there, it will definitely start acting erratically. Yes, friend?
Are there any second order optimization methods used?
Yeah. Second order optimization methods can be used, and some people definitely do use them, but it's not super common because Atom works pretty well out of the box. But yeah, you definitely can. PyTorch can calculate second derivatives for you. But again, it's just not as common just because it requires more compute to be able to do that for like marginally better gradients. But yeah, there's definitely plenty of other fun different tricks that you can do to get better gradient descent like that. Are there more questions? Yes, Fran? Sorry, what was that? Oh, like when to stop training? Yeah, so like again, like say the board's getting kind of cluttered. Like if we're descending this hill, like say up here, like on the y value is the value of our loss, right? So if we're keeping track of our loss at each iteration, so our loss is going to be like pretty high, right? And then we make a bunch of smaller steps after we run through the data set. Say we end up kind of down here, right? Now we have lower loss, right? So our loss is decreasing. It's going to continue decreasing for a while. And at each one of these dots here, you've saved the model, right? It's continuing to decrease. You've saved the model again. You've saved it again. All of a sudden it gets down here and it starts going crazy, right? And the loss increases again. You've saved the model here. So, just use that instead. So it's important to keep track of your training history, how well your model is doing on its training data, the data that it's training on, and how well it's doing on new data that it hasn't seen before. So that you can effectively figure out which one of your checkpoints is the best. Does that answer your question? Are there more questions? All right. So that is the fancy optimization trick that is prolific, like just everywhere in deep learning, Adam. So moving away from optimization, this is just something you can add in. You can think of it almost as a layer, like we had linear layers before. Batch norm is just something you can do at the end of every linear layer. That just helps your network train a little bit better. So in general, with our network, when we're inputting the data, it's sometimes frequently important to normalize your data so that all the values in your input are in about the same range. And the reason for this with neural networks, is because when we run gradient descent, if our data isn't generally in about the same range, you get sort of like loss surfaces that look like on top, where it's very elongated. And we're going to get some of that kind of like bouncing behavior. Whereas in the bottom, if you have normalized all your features, you're going to get much more sort of regular looking loss surfaces. They're far easier to descend down with gradient descent. Yeah, it makes life a lot easier when at each layer, or not each layer, when with our input data, our features are normalized. That helps sort of the loss surface. That helps our gradients in the first part of the network. But the problem is, like halfway throughout our network, we have no way of controlling whether our features predicted are of like wildly different orders of magnitude. And we'd really like for our activations, like halfway through the network, at the end of each linear layer, to be, like somewhat normalized, so that when we calculate our gradients and take all of our partial derivatives, they aren't crazy and erratic. So we're going to basically, at the end of every single linear layer, subtract the feature or the per neuron mean and divide by the standard deviation. So for each neuron, we're going to look at that entire that batch. We're going to look at all the activations across the entire batch for one specific neuron, subtract the mean of all of those neuron activations, that neuron's activations, divide by the standard deviation, so that we effectively normalize across the batch for every single activation on our neural network. Sort of a weird concept. And after that, we're going to then allow our network to basically rescale those values as it sees fit by multiplying each weight by some value gamma, which is the learned parameter that our network is allowed to control, and add the bias. So this is a very strange concept, but the thing I want you to take away here, what's happening is by default, before our value of gamma and beta are learned, what we're going to be doing is normalizing all of our activations. So we have a neural network, right? And this neuron right here, we're going to look at its value across our entire batch of data, and we're going to normalize it. And if our network wants down the line, if it feels that it's valuable through gradient descent, we can say, you know what, we don't actually need this guy to be perfectly normal. It can be scaled up by a little bit. We can multiply it by a value. We don't actually want it to just be normal. We would like it to be a little bit bigger, or maybe we would like it to bias towards a certain value. Because when we add batch norm, we effectively kill the bias because we've normalized our outputs from a certain layer. And it's like, well, maybe we kind of want it back a little bit. It effectively makes the default for your neural network to have super well-behaved activations so that they're kind of normalized. This is sort of a strange concept. Are there questions upon this? I imagine there probably are. Yes, friend.
By activation, you like really activate.
Yeah, generally the value that we compute at each neuron is like called the activation of that neuron. Sorry, it's kind of confusing. It's not good terminology. The output of any given neuron is what we're going to be normalizing. So we have an entire batch of data that we're going to train on, and we can compute, right, the average the average value computed at this neuron, as well as the standard deviation computed for that neuron across our batch of data. And we're just going to try and normalize that value. And again, our network might not think that that's like ideal. So we allow it to learn to kind of like scale up and add back a bias to that value. Does that kind of make sense? It's sort of a strange concept. Yes, friend. Oh, yeah. Did you raise your hand?
Oh, yeah.
Yeah. Yeah. Again, like we haven't actually added like any expressivity to our model. By normalizing all of our activations and then allowing it to learn to rescale them and rebias them, we haven't actually, the set of outputs that we can compute at any given layer is like literally no different. Like we've added redundant parameters effectively. The important thing is that now with this, the default for your network is to have well-behaved neuron outputs. That's sort of the idea, but it doesn't mean our network can like express new things or anything like that. They're the input to the next next layer. When I say in this context specifically, I apologize for the terminology. That's my bad. The activation is the output of the neuron. So the neuron takes in a bunch of stuff and then it computes a value like 5. 5 is our activation. You can also do batch norm after you've taken your real activation, like the ReLU or any other kind of activation you would like, NH. You're also allowed to do batch norm after you've done like the ReLU or whatever. People go back and forth on which one is better. You can just sort of pick one randomly, and it doesn't really make a huge difference. But yeah, does that make sense? The terminology is clear? Okay. Yes, friend? Yeah, just after every single layer. Just normalize every single neuron's output across that batch. And then again, allow it to rescale it if it wants, but make the default well-behaved outputs. Are there more questions? Okay. Yeah. So again, batch norm is just something you can throw at your network just after every single layer. It simply gives us nicer gradients because our loss surfaces will just look a little bit more like this because all of our values being passed into every single layer are going to be about in the same range, at least by default. And it doesn't allow us to represent anything new. Our function doesn't become any more expressive. We've just made the default setting for our model a little bit nicer. Ensembling. So if you have a model and it's topping out, you think this is about the best you can do on validation data, and you don't think there's really anything you can do, something you can try and do if you have the compute is train a whole bunch of models, and hope that you get sort of the wisdom of the group. If you have a model that's working really well, you can initialize that model a whole bunch of different times, train it up, and simply average the predictions across all those models. This doesn't get you a ton of extra performance, and it normally takes a lot of extra compute because now instead of training one model, you're training like 5 or 6 different models and then averaging their predictions. But it can give you slightly better results if you want to squeeze a little bit more performance out. And it's, again, just this idea of wisdom of the group, decreasing the variance, increasing the bias of your model by a little bit. Yeah, this is something you're probably never going to do, but it's just, I feel like something that you should know about happens. Does anyone have questions about this little weird thing that people do if they have a lot of compute? Dropout, this is used a little bit more. So if overfitting is a problem, before you go and train that batch of data, you can simply choose a whole bunch of neurons to just act and send to 0. And why would this work? So say a neuron during gradient descent isn't sure which one of the neurons before it is going to be sent to 0 or not. It's going to have to learn to use all the features that came before it, all different kinds of combinations of them. So say you're like classifying an image, and say like the last layer neuron corresponds to like different things, like maybe something that has legs, or something that has like red hair, or whatever. If some of these are axed out, you're going to have to learn to figure out, classify your output based on different kinds of information, different combinations of information. You have to learn how to tell the same thing in multiple ways, because you're not going to have complete information from the layer before you. So it just sort of, yeah, it makes you learn the same, it makes each neuron have to learn the same output, given different combinations of input, and only those combinations. So this is something you can just do at the end of every single layer, and it increases regularization, it increases the bias of your model. It makes it a little bit harder to overfit on specific neurons. It makes it more difficult for one given neuron to depend heavily on the output of just one specific neuron that came before. Other questions or comments on this? Okay. So it's sort of another way to get the wisdom of the group effect, and that you have to learn the same thing multiple ways. Yeah. Skip connections are the last thing, I believe. And if we have time, I can show you a little bit of PyTorch, but skip connections are the one last thing. So say you have a super deep network with like 50 layers, and say about halfway through, you have enough information to accurately classify the input, for instance. The problem is that you have half the network to go, and you have to very carefully select your weights and biases for all of those layers that come after, so that your perfect information doesn't get like obfuscated or confused, or permuted as you keep going. It doesn't get noisier as you go. It's a question of like, at a certain point with our standard model of a neural network, you can only go so deep before you start getting worse and worse performance. And we want to make it really trivial, so that as you can just sort of stack arbitrary amounts of layers with like no consequences. And skip connections sort of allow us to do this, because if you look at what this formula is doing, so we have this block, right? You take in an input, you run it through a bunch of weight layers, and then after that, you simply add the input, the identity. So if you want to make it really easy to continue to pass a message without it getting confused, if you want to learn the identity layer to be able to just output whatever you took in, without adding noise to the information you have, you can simply learn all the weights and all the biases to just be 0. It makes it trivially easy to figure out how to continue to propagate information forward. If you feel like at a certain point in your network, we have all the information we need, we're good to go. So the important thing about a skip connection is it allows you to learn in this block here. You simply just take a bunch of blocks and just stack them on top of each other to create your network, or stack them one after the other, rather. Is it allows us to learn the identity function. Oh, I jumped the gun a little bit when I was talking, but yeah. If you're ready to classify halfway through your network, if you have skip connections, all you have to do is learn zeros for all the weights, which is trivially easy. And then you can pass your good information all the way to the very last layer, which will classify for you correctly. We can build arbitrarily deep networks with like no consequences now. You can just Hail Mary it and just keep adding layers. Big networks go burr. It's that simple with skip connections. And they are used everywhere. So basically what today is we wanted you to learn like these tools, which is prolific. And you will see them in all kinds of models. We're going to see them lots in our computer vision models, but they're used all over the place in like natural language processing, all of these different tools. And these are just things that you have for your toolkit now. If you're building a network, you can just add these things to your existing network to try and like boost performance and make it better. I didn't have enough time to get to PyTorch, but it is on the homework, which I think explains it pretty well. If y'all want to disperse, that's totally fine. I will continue to stay here and talk about this for a little bit more. It's only a couple of slides. The basic idea, backprop is super hard. We want something that will compute derivatives for us. What PyTorch can do is it can calculate the derivative evaluated at a certain point. It cannot calculate like the symbolic derivative. It doesn't know what the derivative of x squared is, but it can tell you what the derivative of x squared is at a certain value. And if you know how to use NumPy, PyTorch is going to be really, really easy for you because it basically just looks like NumPy with extra bells and whistles on it. So PyTorch, just like you would import NumPy, you're importing that. Rather than creating NumPy arrays, you're going to create torch tensors, but it's literally the same thing. So we can create functions and stuff. And it literally, it looks exactly the same. You can take these things, square them, add them, subtract them, whatever. But if you create a function that takes in a value, squares it, and returns it, we can actually calculate the value of the gradient on a certain input. That's basically what PyTorch is doing. It is like fantastic. So with that, I think we're done. Got through all the slides. Yeah. I will stay up here for questions.